Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is Module 14 in our Circuits 2 lecture series where I'm going to discuss Bode plots. And in, current times, I guess, we typically use computer tools to plot the frequency response of circuits with capacitors and resistors and inductors. So we've already seen how you can use tools like MATLAB and SPICE to determine the frequency response of circuits. And this is really a very common sort of industry standard method. Bode plots are actually a way of generating these frequency response plots by hand. And this Bode plots are a very old technique, and they came into widespread use before the advent of these very convenient and powerful computer tools. And so in many ways, Bode plots have been eclipsed by the sort of onset of modern computer analysis software. However, it is still worthwhile to look at them at least a little bit because they do give you a little kind of an intuitive understanding of how to predict very quickly and roughly predict the frequency domain response of a circuit just by looking at its transfer function equation. And so in general, a Bode plot can show either the magnitude or the phase of our transfer function versus the log of frequency. And typically, magnitude is plotted in dB. Now, because I'm going to sort of give you kind of an abbreviated overview of Bode plots, we're not going to bother looking at phase in this module. And I should also say that Bode plots can be generated for second-order circuits, circuits with a second-order Laplace transfer function, for example, but we're going to look at only first-order circuits, just to give you an idea of what the Bode plot technique is all about. But just be aware that if you do sort of get into this and want to go further, you can also accommodate second-order transfer functions as well. So when creating our Bode plots, we will be working with transfer functions that have this basic general form. We have, first of all, a term k, and k is a real valued constant. We then have a j omega term that can either have an exponent of +1 or -1. So in other words, if j omega has an exponent of +1, it's on the numerator of our transfer function. And we call this term 0 at the origin. And the reason why we call it a 0 is because it causes our transfer function to be equal to 0 for an omega radial frequency of 0. If this exponent is equal to -1, we have 1 over j omega, and we call this a pole at the origin. And the reason why we call this a pole is because when we have omega equal to 0, it causes our transfer function to be equal to infinity. And if you plot the magnitude of the transfer function as omega gets smaller and smaller and smaller, and as it approaches 0, you'll see that transfer function sort of shoot up until it goes actually up to infinity at omega equal to 0. And that sort of quick sort of spike upwards of the transfer function looks like a big pole, basically. And so that's where the name comes from. Now, we then have our numerator consisting of a product of a bunch of different terms with this same kind of form. 1 plus j omega divided by z1 times 1 plus j omega divided by z2, all the way up to 1 plus j omega divided by zn. And these terms on the numerator, 1 plus j omega divided by zn, we refer to these as simple zeros. And that just means as this term gets smaller, it causes the overall transfer function to get smaller. It doesn't often, or it doesn't actually reach zero, because in order for it to reach zero, we would have to have this term being equal to -1, and because it's an imaginary number, it can't be equal to a value of -1. However, we still refer to it as a zero, because as it gets smaller, the overall transfer function gets smaller. And we're going to assume that Zn is real. In general, sort of the broader theory of Bode plots can accommodate the scenario where Zn is complex, but we're not going to focus on that in this module. Finally, we have on the denominator, 1 plus j omega divided by p1 times 1 plus j omega divided by p2 all the way up to 1 plus j omega divided by pm. So we have 1 plus j omega divided by pm. And we call this a simple pole because when this quantity gets smaller, because it's on the denominator, it causes the overall transfer function to get bigger or sort of spike up. And we're going to assume pm is also real. And again, in general, it can be complex, but for the purposes of our module, we're just going to focus on the real valued condition. And so this is the general overall form of our transfer function. Now, you might think back to the lecture that we had on filters, and you can remember sort of us constructing RC and RL and RLC circuits that had, 1 plus j omega times RC, for example. And we're going to be working with those types of transfer functions and putting them in this general form. And that's kind of where we're going with this lecture. But for now, I'm just going to keep this transfer function in this kind of general form. We'll treat it in a very sort of generic and general way just to introduce the idea of Bode plots. And then we'll conclude with some examples that'll hopefully tie it fairly tightly to the transfer functions that we get for actual real circuits. So in general, this transfer function is a complex valued function, right? So we've got an imaginary number here, we've got a real number here, so it's going to be a complex number. And that means that h omega has a magnitude and phase, and also that each one of these sort of individual terms that make up h omega have a magnitude and phase as well. So for example, if we take a look at just the term j omega by itself, it can be represented as a complex exponential where the magnitude is equal to the real part squared, which is just 0 in this case, plus the imaginary part squared, which is omega. And then we have e to the j, and then we have the phase of our complex number. But because this is a pure imaginary number, the phase is equal to pi over 2. And so the overall number expressed in terms of a complex exponential is got a magnitude of omega and a phase of pi over 2. And again, you can create Bode plots that represent the phase of a transfer function. We're not going to focus on it, but it certainly is possible. And of course, when you're simulating the frequency domain response of a circuit in MATLAB or in SPICE, you can look at the phase of the transfer function also. The next sort of general term that we have, both on the numerator and the denominator, takes the form 1 plus j omega divided by some real number alpha. And I'm just going to use alpha in here because when it's on the numerator, we represent that real number with z, and on the denominator, we represent it with p. And so if we represent this number using a complex exponential, the real term is 1. The imaginary term is omega divided by alpha. E to the j tan minus 1 omega divided by alpha. And so this is the magnitude. And this is the phase. So we're just going to focus on the magnitude terms, as I said before. Now we know that when we're working with logarithms, we know that the log of a times b is equal to the log of a plus the log of b. And we know that the log of a divided by b is equal to the log of a minus the log of b. And because of that, if I want to take the magnitude of h omega and express it in terms of decibels, I basically take the log of this entire term. But this entire term is made up of a bunch of stuff multiplied and divided by each other. And so this means that the magnitude of h omega in decibels is equal to 20 log of k plus or minus 20 log, and these are base 10 logs, of omega, plus 20 log of the square root of 1 plus omega over z1 squared, plus all the way up to the 20 log of the square root of 1 plus omega over zn squared, minus 20 log of 1 plus omega divided by p1 squared, minus all the way up to 20 log of the square root of 1 plus omega over pm squared. Right? And so basically, our top expression, the numerator is a product of a whole bunch of zero terms, and so when we take the log of all these products, because of this property of the logarithm, they end up just being added together individually. Because these simple pole terms are on the denominator, we're dividing by them, and so we end up subtracting each one of those terms individually. This omega term, its magnitude is either added or subtracted, depending on whether it is a 0 at the origin, in which case it would be added, or a pole at the origin, in which case it would be subtracted. And this real valued constant k is just, put out front there. And so basically, when we focus on the magnitude and when we express the magnitude in dB, the overall value of the magnitude of h omega in dB is the individual sum of all these terms. And the Bode plot technique is going to take advantage of the fact that we can just add the contributions of all these individual terms together. So the basic idea behind the Bode plot technique is we're going to figure out what each of those individual terms in that decibel summation look like in the frequency domain. And then we're going to basically construct our Bode plot by adding all of those things together, sort of graphically. And so let's get started. The first thing I want to do is go through each one of those terms and figure out what they look like when we plot them. And we'll start with the easiest one. Let's take a look at the constant k, and what it looks like when we plot it versus frequency. Well, when we take the 20 log base 10 of k, we just get the constant k in dB. And of course, this is just a real number, so it's not a function of frequency at all. And so when we plot it versus the log of omega, it's just a straight line. Right? It just looks like that. And it's equal to k dB. Now, let's take a look at a 0 at the origin. So the equation for that is 20 log base 10 of omega. And so this term basically just increases with frequency. It equals 0 when omega is equal to 1. So that's the 0 crossing. And when we plot it versus the log of omega, it's basically a straight line with a slope of 20 dB per decade. And what do I mean by that? Well, here's a plot of 20 log base 10 of omega. So first of all, the x-axis is the log of omega, and the y-axis is the magnitude of h of omega in dB, when h of omega is just equal to a simple 0 at the origin. And so if this is the equation that we're plotting versus the log of omega, when omega is equal to 1, our equation is equal to 0. So this is our 0 crossing. And otherwise, it's a straight line. And the slope of the line is 20 dB per decade. And so a decade, when we're looking at a log x-axis, is basically just the jump from, or by a factor of 10, right? So 10 to the 0, this is 1, this is 10, this is 100, this is 0.1. And so each of these jumps we refer to as a decade. And in one jump of a factor of 10, our straight line goes up by 20 dB. So when we go from 1 to 10, we go up by 20 dB. When we go from 10 to 100, we go up by 20 dB. Versus log 10 of omega. Now we can take a look at a pole at the origin. The equation for a pole at the origin, because it's 1 over j omega, or it's on the denominator, is minus 20 log 10 of omega. And satisfy yourself that this makes sense. So when we're on the numerator, we're adding. We're on the denominator, we're subtracting because it's a division. And other than this minus sign, this is exactly the same formula. So if this is a straight line with a positive slope, this will be a straight line with a negative slope with exactly the same zero crossing. So it's going to equal 0 when omega is equal to 1. And if we take a look at a plot of it, this is minus 20 log base 10 of omega. Our zero crossing occurs at 1. And the slope is still 20 dB per decade. So, or sorry, the slope is now minus 20 dB per decade. So when we go from 1 to 10, we drop from 0 to minus 20 dB. When we go from 10 to 100, we drop from minus 20 dB to minus 40 dB. Okay, now for a simple 0, things are a little bit more complicated. So we have 20 log 10 of the square root of 1 plus omega over alpha squared, where alpha is a real number. Now, the way that Bode plots kind of tackle this situation is we sort of look at kind of the asymptotic cases. We take a look at what happens to the value of this term when omega approaches 0, and then we take a look at what happens when omega approaches infinity. And so when omega approaches 0, what happens is our magnitude in dB approaches 20 log 10 of the square root of 1 plus 0, which is 0, right? Because the log of 1 is 0. And so this term, as we approach 0, approaches, or as we approach sort of the low frequency range, our magnitude is going to approach 0. Now let's take a look at what happens when we approach a really, really large frequency value. So for omega approaching infinity, right? So not there, but we're getting really, really large in frequency. Our magnitude in dB is going to approach 20 log 10 of the square root of omega over alpha squared, which is just equal to the 20 log 10 of omega over alpha. So where did the 1 go? Well, we're assuming that this term is so big that the 1 basically doesn't matter anymore. And so as omega approaches infinity, the 1 drops out, the square root and the square cancel out, and then we have an equation that looks a lot like what we had up here. And this is, just like up here for the 0 at the origin, this is a straight line this is a straight line with a positive slope of 20 dB per decade. Okay, so that's what happens, you know, in the low frequency range and in the high frequency range. So let's take a look at the actual plot and see what it looks like. So here is a plot of 20 log 10. That's not a very nice 2. Be a little more careful. 20 log 10 of the square root of 1 plus omega over alpha squared, where in this case alpha is equal to 2. And so let's take a look at, first of all, the low frequency range. So, you know, 0.1 hertz, 0.01 hertz, like this, very, very small frequencies. Very, very close to DC. And we can see that our response asymptotically is approaching 0. And if we take a look at larger frequencies, so 10 hertz to 100 hertz, we can see that we get a line, a positive line, with a slope of roughly 20 dB per decade. So here we're at about 15, almost 15. Here we're at almost 35. So we're not quite 20 dB per decade, but it looks pretty close. And in between here, we sort of have this kind of curvy response, right? And just to point out this location, this is, oops, sorry. This is 2. This is the value of 2, which is our value of alpha. And so basically the way Bode plots work is we say, all right, we recognize that for the low frequency range, we have something that looks a lot like a flat line at 0. For the high frequency range, we have something that looks a lot like a line with a slope of 20 dB per decade. So we're just going to represent this plot as using those two lines. And the two lines are going to meet at the alpha, or the frequency value that's equal to alpha. And we call this the corner frequency. And if I were to just kind of draw this in, so we locate the corner frequency, which is equal to alpha, and then to the left of the corner frequency, we approximate our frequency response using a flat line at 0. To the right of our corner frequency, we represent the frequency response as a line with a slope of 20 dB per decade. So here at 2, we have, we're at 0. This is 20, which is a factor of 10 bigger than 2. So from here to here is a decade. And so this is where our line of 20 dB per decade would be. And then if we connect those dots, it looks like that. And you can't see it very well on this plot, but basically, you know, this line would gradually start to approach that line. So again, the dark line shows the actual frequency domain plot. I generated this in MATLAB. And then the orange line represents our Bode plot approximation of that frequency response. Okay, so then just to kind of summarize this, to approximate the response due to a simple 0, we basically have to do, I guess, 3 things. So the first one is find the corner frequency. So find the corner frequency alpha on your log-log plot. Draw a line at 0 for all frequency values less than the corner frequency, and then draw a line with a slope of 20 dB per decade for all frequencies above alpha. And of course, the two lines meet right at alpha. So the final case we have is the simple pole. And this is exactly like the simple zero, except that it's got a negative sign in front of it, so we can go a little bit faster on this one. So as you would expect, as omega approaches 0, the magnitude in dB also approaches 0, just like it did for the simple 0, right? So the negative sign doesn't affect that. And then as omega approaches infinity, the magnitude in dB approaches 20 log, minus 20 log 10 of omega divided by alpha. And if this isn't clear, it's exactly the same as the simple zero. The only difference is we have a negative sign in front. And so if we are to take a look at a plot of minus 20 log 10 square root of 1 plus omega over alpha squared for alpha equal to 2, what we do is we locate alpha equal to 2, which is right there. We then, for frequencies less than alpha, we approximate the frequency response as a straight line at 0. For frequencies greater than alpha, we approximate the frequency response as a straight line with a slope of 20 dB per decade. So this is 2. This is 20. Right? So that's our decade. We go to minus 20 dB in this case, because our slope is negative because of this negative sign. And then we draw our straight line. And it looks like that. And just to summarize this, to approximate our frequency response, it's exactly the same procedure as for the simple zero, as you just saw. We find the corner frequency. We draw a line at 0 for the frequency values less than the corner frequency, and draw a line with a slope of minus 20 dB per decade for omega greater than alpha. Okay, so now the best way to illustrate how this all kind of fits together to allow us to determine the frequency response of an actual transfer function is to use an example. So, for our example, let's consider a frequency response h omega, which is equal to 3 times j omega divided by 1 plus j omega divided by 4. I'm just giving you an example just with some actual numbers plugged in here. In a little bit, I'll show you how this kind of relates to sort of the RLC transfer functions that we've been kind of deriving up until now. But let's just use this as a starting place. So if I wanted to express the magnitude of this frequency response in dB, it would be 20 log times the constant. So 20 log base 10 of 3. So that takes care of this constant in front of the transfer function, plus 20 log of omega. This term takes care of the 0 on our numerator, minus, and these are all base 10, minus 20 log base 10 of the square root of 1 plus omega over 4 squared. And so these are the three terms corresponding to the constant, 0 at the origin, and simple pole. And basically what I want to do next is to plot the frequency response for each of these three terms by themselves. And then the overall frequency response is just going to be the addition of all of those three plots. Okay, so here we have three plots, and I'm going to put on the top plot the plot of k expressed in decibels. The middle one's going to have 20 log base 10 of omega, and the bottom one is going to have minus 20 log base 10 of 1 plus omega over 4 squared. And on each plot, I've located the frequency of 1 and also the frequency of 4, because those are both going to be important. And so when we express 3 in decibels, we get a value equal to 9.5 dB. And of course, this is just a real number that is not a function of frequency, so it's a flat line. The simple 0 at the origin is a straight line with a slope of 20 dB per decade. That crosses, that zero crossing occurs at 1 hertz when we're plotting versus the log of omega. And then to approximate this simple pole, we locate the corner frequency, which is 4. For frequencies lower than the corner frequency, we approximate the response as a straight line at 0. And then above the corner frequency, we have a straight line with a slope of negative 20 dB per decade. And what we're going to do is we're going to just add these three curves together. Okay, so the first thing I want to do is add together the curves of our 0 at the origin with our simple pole. And let's start by looking at everything that happens below the corner frequency of 4. So below the corner frequency, our simple pole is equal to 0. So if we add 0 to whatever's going on with our positive line here, we just get the positive line. So for frequencies less than 4, we just have exactly the curve up here. And it crosses through 1, has a slope of 20 dB per decade, and it goes all the way up to the corner frequency of 4. However, once we hit the corner frequency, what happens is we now have a negative line with exactly the same slope as our positive line. So these two actually cancel out, and our frequency domain response remains constant after that. And we have to figure out the magnitude where we sort of switch to this constant value. Let's call that K1. And K1 can be determined just from the slope of this line. So we know this is 20 dB per decade. And so that's rise over run. So we just multiply it by, and we know that our zero crossing is right here. So we just multiply our slope by this amount. However, the only thing that you have to be careful of is because this is in the log scale, we take our slope of 20 dB per decade, and then we multiply it by the log base 10 of 4. And when we do this, we get a value of 12. And so this levels out at 12 dB. Finally, we need to take this and just add it to the 9.5 dB offset that's caused by our constant. So that doesn't change the shape of our frequency response. We're still going to have this increasing line, and it's still going to flatten out. We just shift everything up by 9.5 dB. And so our final plot looks like this. So at 1, we used to cross at 0, or sorry, this used to be our 0 crossing, but now our line is going to be at 9.5 dB. We're going to go up, and we're still going to flatten out at 4, but this point is going to be at 12 plus 9.5, or 21.5. And that's our result. So we know exactly what our, well, not exactly, because this is sort of an approximation, but we know what our magnitude response looks like in the on a dB scale versus the log of frequency. And we can see this is basically a high-pass filter, right? We attenuate signals at the lower frequencies, and then at the higher frequencies, we have a nice flat response. So of course, the whole point of this Bode plot stuff is to come up with quick approximations for the frequency response of the transfer functions that we derive for circuits. And up until now, we've been using this kind of generic Bode plot sort of transfer function format. And I just want to conclude with a few quick examples showing how you convert the kind of standard circuit transfer functions into something that's kind of Bode plot friendly, I guess. And so the first example is our now very familiar RC low-pass filter. And we know our transfer function h omega is equal to 1 over j omega RC plus 1. And in this case, we just have one simple pole, no zeros. And if we translate this into our Bode plot form, where we have a constant k in front, and we have one simple pole, which has the form of 1 over j omega divided by alpha. In this case, k would just be equal to 1. And the corner frequency, alpha, would be equal to 1 over RC. And this is kind of a useful result, right? Because when we are designing RC low-pass filters and we want to have just kind of a quick, rough estimate of the cutoff frequency of our low-pass filter. This corner frequency is a good estimate. So if you say, okay, I want a cutoff frequency of 8 kilohertz or something like that, you would choose your R and your C components so that 1 over their product was equal to 8 kilohertz. So that's kind of a nice sort of rule of thumb to use when you're designing these things. Another example is an RL high-pass filter. In this case, H omega is equal to J omega L over R over J omega L over R plus 1, right? So this is sort of the form that we have from our kind of circuit analysis results in module 13. And so we need to, we now have a simple pole, and we also have a 0 at the origin. And so to convert this into Bode plot form, we have 1 pole, or 1 0 at the origin, and then 1 simple pole. And so in this case, K is equal to L over R. So we just took L over R and we put it to the front of the circuit, so J omega can stand by itself. And the corner frequency or if you like, the cutoff frequency of our high-pass filter, alpha is equal to R over L. And then once you have it in this form, this would be exactly the same example that we just worked through, where I had the number 3 here and the number 4 down there, but we would have basically 3 curves that we add together, an offset K, positive, a line with a positive slope of 20 dB per decade, and then the simple pole result where we're 0 until the corner frequency, and then we've got a negative, a slope with a negative slope, or a line with a slope of negative 20 dB per decade. And up here, this is a nice easy one because K equal to 0, or sorry, K equal to 1 is just 0 when expressed as decibels, and we only have one simple pole, so our frequency response would be basically flat until the corner frequency, and then it would just go down like that, and we wouldn't have to really add kind of anything together at all.